Welcome to my lecture series. Today my topic is standard representation of logic function. We know that in our digital system design there is Boolean expression. Boolean expression is often known as standard representation of logic function is of two types. One is SOP, another is POS. SOP stands for sum of product and POS stands for product of sum. So any logical function under Boolean expression can be represented in terms of SOP and in POS form. Now we can see that the standard representation of SOP, how we can represent any logical function in SOP form. So by its name we can definitely understand that sum of product, that means there should be first AND operation, and with that AND operation there is OR operation. So for example, AB plus ABC complement plus C. This is an example of SOP form where we can see that these are all AND operation, and after that we are doing OR operation. Now what is POS form? If we represent this particular expression in POS form, then we can write as A plus B, A plus B plus C complement into C. So we can see that first there is OR operation, after there is AND operation. So basically this is the standard representation of logical function which can be represented as in two ways, SOP, POS, and the example of this I can show you. Now our next part is that the canonical form of SOP and POS. Now what is canonical form? For example, Y if we consider the previous expression, we can see that so this is nothing but an SOP expression. Now this is not in the canonical form of the expression. Now why? Because here we are having the variables A, B and C. So total 3 variables are there. But in this expression, in each term, we can see that here C is absent in the first term. Here all the variables are present, and here A and B, these two variables are absent. So we cannot say that this is the canonical form of the expression. Now our task is to convert this expression in the canonical form. How we can do it? Let's see. Now which variable is absent here? C variable is absent here. So we can do what? C plus C complement. Again A, B, C complement plus, here we can see that A and B, these two variables are absent. So we will multiply C with A plus A bar and B plus B complement. So now, why this is so? Because C plus C complement will give us 1. So if we multiply 1 with anything, that doesn't make any difference to particular expression. Now what is the final expression? A, B, C plus A, B, C complement plus A, B, C complement plus A, C plus A complement C, then B plus B complement. Again, in the next step, we can write as A, B, C plus A, B complement C plus A complement B, C plus A complement B complement C. So this is the, now we can say that this is the canonical form of this expression where all the variables are present in each terms. Now we can see that we will check which variable or which term is repeated here. So we can see that here ABC complement is there, again ABC complement is there. Without this, ABC is there and ABC is there. Now in short we can write ABC plus ABC complement plus AB complement C plus A complement BC plus A complement B complement C. So this is the final canonical form of this logical expression, and this is obviously in terms of SOP. Fine. So now we will check how we can find out the canonical form of POS. So again, Y, A comma B comma C, that is the function of these three variables, A plus B into A plus B plus C. This is one kind of a POS example. Now again we will first check to find out the canonical form of this expression, that which variable is absent. So in the first case, A plus B is there, C is absent. In the second case, all the three variables are there. So we have to add why we are adding C dot C bar? As C dot C bar means, so adding 0 doesn't make any difference to that particular term. So now it will be So that is the canonical form of the expression of this. Now we have to check that which expression is repeated. So we can see that these are repeated. So in short we can write as this is the standard form of this particular expression, which is again in terms of POS expression. Now come to the part min term and max term. So min term is related to SOP, min term is related to SOP and max term is related to POS. For example, if we consider this equation, this is nothing but the SOP, and we can see that in every terms all the three variables are present. Now how we can find out the min terms of this particular expression? First take A, B, C. In min terms or in SOP, if it's in normal form of these variables, it will be written as 1, 1, 1. So 1, 1, 1 means M7. Now what is the next term? That is A complement B, C. So as it's A complement, it will be written as 0, 1, 1. 0, 1, 1 is nothing but M3. Next expression is A, B, C complement. So it can be written as 1, 1, 0. So 1, 1, 0 means M6. A complement, B complement, C complement. It can be written as 0, 0, 0. So it will be M0. Now these are the min terms of this canonical form of the expression. So in short we can write it as y function of a comma b comma c is equal to summation small m. What are the min terms we have found? That is 0, 3, 6, 7. We have to write in this way. Now these are the min terms expression of this logical expression. Now why we will find out the min terms? Because through this min terms expression we can put it into the K-map, which is known as the Karnaugh map, and through that Karnaugh map representation we can find out the shortest form of the equation. Now come to the part that is, now this is our min term expression. Thank you.